Rust forming, a battery driving your phone, metal being plated with gold, all the same hidden event. Electrons moving from one substance to another. Master where the electrons go, and a whole branch of chemistry that looks like memorizing turns into simple bookkeeping. This unit is the accountancy of electrons. This unit follows those electrons. We define oxidation and reduction by electron movement, invent oxidation states to track them like a scoreboard, write half equations for each side, and finally force reactions to run backwards using electricity, electrolysis. One idea, electron transfer, threaded all the way through. First stop the two halves of every redox reaction. Oxidation is loss of electrons, reduction is gain. The classic memory hook is OILRIG, oxidation is loss, reduction is gain. They always happen together. One substance can't give electrons away unless another is there to take them. No lone oxidation ever. Picture zinc dropped into copper sulfate. The zinc atoms hand 2 electrons each to the copper ions in solution. Zinc loses electrons, so zinc is oxidized. Copper ions gain them, so they are reduced to copper metal. The electrons literally move from zinc to copper, and the blue solution fades as the copper plates out. That's redox you can watch. Tracking electrons one by one gets fiddly, so chemists keep score with oxidation states, a number for each atom saying how many electrons it has gained or lost compared to the free element. A few rules nail almost everything. Free elements are 0, simple ions equal their charge, oxygen is usually -2, hydrogen usually +1. 2 payoffs make this worth it. In any neutral compound, the oxidation states must add up to 0, so one unknown always drops out. That's how you find sulfur in sulfate. And the rule that names the reaction? If an atom's oxidation state goes up, it's been oxidized. If it goes down, reduced. The scoreboard tells you instantly. Next, half equations. Write each side of the transfer separately, electrons and all. The oxidation half shows electrons being produced. The reduction half shows them consumed. Zinc to zinc 2 plus releases 2 electrons. Copper 2 plus 2 electrons becomes copper. Each half is its own tidy little equation, electrons made explicit. The trick to combining them is the electrons must cancel exactly. Scale each half so the number of electrons lost equals the number gained, multiply up if you must, then add the halves together, and the electrons disappear from the final equation. Balanced electrons, balanced reaction. That cancellation is the whole game. Now we run redox in reverse. Some reactions won't happen on their own, so we push electrons in with a power supply. That's electrolysis. Dip 2 electrodes into a molten or dissolved ionic compound and switch on the current. Positive ions crawl to the negative cathode, negative ions crawl to the positive anode. Electricity does the forcing. At the electrodes, the transfer happens. At the cathode, positive ions gain electrons, reduction, pulling metal or hydrogen out. At the anode, negative ions lose electrons, oxidation, often releasing a gas. A neat memory aid, reduction at the cathode, both begin with consonants that pair up. Same redox rules, now driven by a plug. Finally, predicting the products. With a molten compound, it's simple metal at the cathode, non-metal at the anode. In water it gets interesting, because water itself can react, so you must ask which species is easier to discharge. Often hydrogen comes off instead of a reactive metal, and oxygen instead of a stubborn ion. And there's a payoff beyond the exam. Electrolysis is how we extract reactive metals like aluminium, purify copper, and electroplate cheap metal with a precious skin. The same electron transfer that rusts a nail, run deliberately and in reverse, builds the modern world. Follow the electrons and it all connects. Here's electrochemistry on one page. On the left, the language of electron transfer, oxidation is loss, reduction is gain, oxidation states keep the score, and half equations split the two sides. On the right, electrolysis, reduction at the cathode, oxidation at the anode, driven by a power supply. Your drill, assign oxidation states to spot what's oxidized and reduced, write each half equation, then scale so the electrons cancel. Electrode potentials, putting numbers on how badly each species wants electrons, come at a 2 and build straight on this. For now, you can follow every electron in any reaction.